Thank you.
Now, we're gonna lock the front door. All right, we're now going to talk about Nick's class. Now, you people probably know that, or you've heard of the rule that everything, computation speed doubles every 3 hours or whatever, 3 years or whatever it is. But eventually that has to end because there is an absolute limit to how many computations could be done by a processor in a certain amount of time. Because processors can't be any smaller than the smallest particle in the universe, and the internal computation can't go any faster than the speed of light, so that puts a limit on it. However, we can vastly increase the computational power of computers by having many processors working together. Then the question arises, if we have a problem that takes 1 trillion years to solve with one processor, can we solve it in 1 year with 1 trillion processors, or perhaps more than that? But is it possible to divide a problem up in such a way that many processors can work on the problem simultaneously and accomplish it in a lot less time? Well, this introduces the concept of Nick's class. The answer, by the way, to that question is no one knows. However, experts believe that it is not always possible. All right, now Nick's class is all the problems where you can break it up. So we can define Nick's class to be a set of languages, those languages which can be decided by polynomially many processors in polylogarithmic time. All right, now what do I mean by that? I mean O of n to the k processors and O of log to the power of k n time. So relatively little time and not too many processors. All right, now these classes, this is of course NC, Nick's class, which is named after Nick Pippinger. Nick's class is a computational class, illustrated here in the Euler diagram by this oval here. It contains the context-free languages, so every context-free language is in Nick's class. And every regular language is context-free, which means that if we have a context-free language and we have a string, it is possible to decide whether that string is in that language, given the grammar, in polylogarithmic time with polynomially many processors. All right, now, inside Nick's class is inside the polynomial class P, which is abbreviation for P time. And of course, no one knows whether NC equals P. That's an open question. Turns out that's a very important question because as a practical matter, we would like to be able to break up problems into pieces so that we could solve them faster. But no one knows whether this is always possible. Now, inside the class, the polynomial class, there's a subset of problems which are the hardest possible problems in the polynomial class. Sort of similar to NP completeness, we call these P complete. And we'll get into more of what that means in the next slide or so. Well, this is an example, an illustration of an arbitrary Nick's class computation. We have an input string here, which has length n, and an output string. Now, it could be 1 bit when we're doing a decision problem, but on the other hand, in general, it could be a string whose length would be a polynomial function of n for sure. And in between, we have a bunch of processors. How many? Well, no more than O of n to the k processors. And the whole computation comes down rapidly with all the processors working in O of log to the power of k n time. So if this is true, we say that f is an NC function, or f is NC, that function. Now, one example of such a function is sorting. If we put in W is an array here, then we could have f of W be a sorted array with the same items. And then it is possible to construct such a scheme. We could call that a computational structure, which will cause this thing to be sorted in the output. That's only one example of such a problem where that can be done. Now, for example, this is a very tiny list of problems where it is possible to solve the problems with an NC computation. Here are some examples: sorting, addition. Now, we're talking about adding numbers that are n bits long. Now, when we talk about the size of an input, we refer to the number of bits. So a binary numeral for example, a trillion, has size 9. Well, that's not very large, but there are practical situations where we're interested in bits, in numbers where there are many bits, very large number of bits, and then that number of bits is the size of the problem. Now, we can add and multiply numerals that have n bits in NC computation. Also, matrix multiplication can be done in NC, and there are many other problems of practical interest. How about all of them? Well, of course, if a problem is not polynomial, it can't be NC. However, if it is polynomial, it might not be NC. No one knows for sure. It's an unsolved problem. Remember in the diagram, I had a set of problems which I called P-complete. These are the hardest problems in the polynomial class, in the sense that they are the problems that are, well, hardest in the sense of NC reductions, meaning that if any one of these problems is an NC, then NC equals P. It's an analog of NP-complete. Now, one problem that's known to be P-complete is the Boolean circuit problem, and I'm giving you two different pictures of that. You've heard of AND gates, OR gates, and NOT gates. Well, suppose we have a big acyclic graph of AND, OR, and NOT gates. And then at the end we have a single bit output. And each, we can have, for example, 1 and 0 coming in. And what we're interested in is what the output bit is. Now, that problem can easily be solved with dynamic programming. Simply look at the gates and evaluate their outputs in topological order. So that means, trivially, the Boolean circuit problem is in the polynomial class. However, no one has been able to prove that it's in Nick's class. And we know that if it is, then all of P is in Nick's class. Here's another way to look at the Boolean circuit problem as a program. We have n Boolean variables. We set x1 to true, x2 to false, then every other variable set equal to either the conjunction or the disjunction or the negation of one or two of the previous variables. And what we want to find out is whether that last variable is true or false after we evaluate all of them. That is clearly possible to evaluate. It's clearly possible in linear time. O of n time it can be done. But what if we had many processors? Could we do it faster? And that is, in fact, also the Boolean circuit problem. And so what we know is that if this one can be done faster, every polynomial class problem can be solved in NC time.